And here we go. Okay, dropped frames, my bitrate is okay. Am I streaming? Yep, I'm streaming. Okay, cool. Okay, so right now this is the first time I'm using OBS for streaming. Before this I've been using, Before this I've been using Streamlabs to, stream my homework. Right now I'm testing out OBS, so everything would be using, the same application. Alright, and is anyone in chat right now? No one seems to be in chat. It's alright. Frames, I don't think any frames has been. Okay, no frames has been. There's no struggling frames. Alright. Here we go. So we have two problems today. We have this one, 7.14 from Donald Taylor's Classical Mechanics. And then we are gonna have 7.21 also for Southern Heaven. Welcome to the stream. Welcome to the stream. First person there. Alright, welcome to the stream. We're doing a classical mechanics problem. We're using the Lagrangian mechanics. There's not gonna be too many questions today. Only two problems, but it should be fine for a relatively short stream. Alright, so let's just get to it, I suppose. Okay, so figure 7.12. Oh yeah, fun fact, OBS streaming using OBS as opposed to a Streamlab actually is helps me a bit because I can copy the stream link before I even start streaming, which as opposed to Streamlabs OBS, which means I don't have to waste my first few minutes of the stream promoting or like sharing my links. So let's get to it. So figure 7.12 shows a crude model of a yo-yo. A mass string is suspended vertically from a fixed point, and the other end is wrapped several times around a uniform cylinder of mass m and radius r. Alright, so this guy has mass m. When the cylinder is released, oh that's great, yep. When the cylinder is released, it moves vertically down, rotating as the string unwinds. Write down the Lagrangian using distance x as your generalized coordinate. Find the Lagrange equation of motion and show that the cylinder accelerates downwards with x double dot equals to 2g over 3. The rest I'll explain as we go. Well, 4 people on the stream. Hello, welcome guys, welcome. Yep. So, first of all, this is how we're going to use the Lagrangian mechanics. First, Lagrangian mechanics, to solve it, of course, we have to write out the Lagrangian. The Lagrangian, typically, although not always, but it's most of the time. The dark freaking circles. Yeah. Most of the time, the Lagrangian takes on the form of T minus V. In this case, T is the kinetic energy. I don't know why they use T. I think it's translational. And then they use V for potential energy. I don't know why they use V for potential energy either. I'm guessing it's because I'm guessing kinetic energy means T means translational. I'm guessing though. V means like voltage, and like in electricity, in electrodynamics, the voltage is basically the potential energy per charge, the potential energy per charge. So I assume that's why the Lagrangian is what it is. I blame rotation for how I remember the Lagrangian formula. Nice, great, you remember the Lagrangian formula. So let's solve this one, shall we? So first of all, using the distance x as our generalized coordinate. So here's the strategy. All right. Let's first write out, what shall we write out? T and V. I reckon V might be easier to write out. So, first of all, I'm going to say that over here, up here, is the point where the potential energy is 0. Now, as we all know, the potential energy the potential energy for gravitational acceleration is mgh. But in this case, h here is the distance x downwards. X extends downwards, so this is actually mg minus x. Because h is how far above v equals 0 we are. And as we go further downwards, x increases. So the potential energy v here is equal to mg minus x. Oh, well, mg times minus x. Or negative mgx, same thing. Now, what we have to do is we have to find the kinetic energy term next. Kinetic energy. Kinetic energy is divided into two parts, as stated in the hint here. The total kinetic energy of a body is 1/2 mv squared plus 1/2 I omega squared. Let me just move this real quick. Move this over here. So, kinetic energy, we're going to split it into two parts. Should we also include the radius from the reference position? Radius from, yeah, actually, let's see. Okay, how about we just define that x here is the distance from, hold on. How about we just define that x is the distance from here to the center of mass. So we don't have to factor in the radius. How about that? I think that we can do that, right? Yeah. Yeah, ultimately it's offset by like plus r, so I don't think that matters much. Because this object, the center of mass is just r over there. I think we should, yeah. We don't have to like add r. In fact, we can add r to x over here, but ultimately, once we put it into the final equation, the r is going to be eliminated because the final equation you're going to have to take a bunch of derivatives, so the r is going to be removed anyway. Oh yeah, that would work too. All right, so kinetic energy. Right, kinetic energy we have to divide into two parts. Of course, the first part is 1/2 mv squared, and the second part is 1/2 I omega squared. So let's take a look what each of these mean. So first of all, 1/2 mv squared is simply just 1/2 times the rate of change of x, because x is the velocity. So x dot here is the velocity, of course. I see. Wait, is chat working? Actually, no, wait. I forgot to add in the, hold on, I'm sorry, guys. Hold on. Chat, I forgot to add in the chat thing. Wait. OBS, how to add chat overlay. For YouTube. I completely forgot about the live chat. I'm sorry, guys. How to add YouTube chat, launch YouTube in a browser, open your YouTube channel, go live. Stream elements and shit. Wait. Okay, you know what? You guys can see the live chat. I hope you guys can see the live chat. Give me a sec. I'm sorry. I completely forgot about this. Hey, Streamlab OBS does this. Streamlab still have that, right? Log in with YouTube. I think I can use one from Streamlab. Even though I'm not streaming directly from Streamlab, I think I should be able to. I think you should be able to add in the browser source from Streamlabs to add in the chat messages overlay. Where is it? Recent events. Streamlabs. How do I dashboard? There it is. Widget. How do I? Oh, if I don't stream your Streamlab, it's gonna. I don't think it's gonna show the. Yeah. Okay. Wait. Is it working? Wait. Let me copy widget URL. All right. Let's see if this works. I hope this works. Chat overlay. Boop, and then I paste that there. Boop. And now I test it out. Boom, test. And chat appears there. Yay! That's first try, baby. First try. Okay. Normally it takes quite a lot of tries for that to work. Ooh, wait, I have a lot of latency. Wait. I just realized how much latency I have on my stream. Okay. It's like 15 seconds of delay. But I think that's tolerable. Hold on. And does it show up? It should show up in a bit. There's a bit of a stream delay, certainly. Yeah, the stream delay is quite significant. I should have put it on low latency. Aw, I don't think I can change it now. I'll change it for the next. Wait, I can change it right away. Wait. Hey, the chat works. All right. Okay, wait, guys. Gonna reconnect for a few minutes. Or not a few, just a few seconds. Yeah. Okay. And we should now have a fairly low latency. I set it on the OBS settings. Yeah, it's showing up now. Perfect. All right. Moving on. This is +1 over 2I omega squared. Are we back? We are back. All right, and the delay isn't okay. The delay isn't much. Perfect. So, if this object is falling down, what is omega here in our case? How is omega related to x dot? Okay, first of all, actually before that, let me just change this to 1/2 mx dot squared plus 1/2 I. What is I? I is the moment of inertia of the cylinder, which we happen to be given the exact formula for it. So that's really convenient. Gonna plug that in there, and then we multiply by omega squared. Okay. Now, what is omega squared? Omega squared is the angular velocity of this is the angular velocity of this cylinder here, of course. So as it falls, as this thing falls down, it's gonna unravel the string and makes it go down faster, right? It's gonna unravel the string that is attached to it. That's like around it. It's gonna roll down, and the result is that sorry, the length here, x here, is gonna be increased by how much? By how much this thing rolled, by the angle that this thing rolled. So dx here is going to be equal to this. It's going to be equal to this length. Wait, yeah. So like from here, let me just from here, and then it spins all the way up here. If it spins up here, it means that this distance here is going to be dx. It's a change in x. So obviously here, this is theta. No, this is d theta. Therefore, we can claim that dx equals to r d theta. What we want to find is omega, which is equal to d theta by dt. So really, what we have is x dot equals to r omega, which is basically this is basically saying that if you roll, the velocity of the object is directly proportional to the angular velocity. and it's multiplied by the r. R equals to, yeah, dx equals to r omega dt. Correct, that is perfect. And so now we know that omega here, okay, wait, hold on, let me zoom in. So we know that omega squared, therefore omega squared is going to be equal to x dot over r together squared, which we plug this right back in here, and we're going to end up with 1/2 m x dot squared plus 1/4 m r squared x dot squared divided by r squared, which you can all cancel out, and we're going to end up with 3/4 m x dot squared. And that is our kinetic energy term. Then we have the potential energy, which is equal to negative mgx. Alright. Everyone's caught up? Perfect. So now let's find the Lagrangian. Okay. We have plenty of space left. So the Lagrangian is, in our case, is equal to the kinetic energy minus the potential energy. Again, this is not always the case. Sometimes it takes a different form, but in classical mechanics, it's almost always like this. Almost. There are exceptions. I couldn't think of them, but I'm not gonna claim that it is universal. There's the case. For example, in electromagnetism, where you have forces that is related to the velocity. In that case, you can't really express it in terms of potential. So the Lagrangian is going to take on a different form. It's still technically potential because you're using the vector potential, but that's a little bit of a side tangent. I'm going to focus now. And this is subtracted by minus mgx. So the minus here means the minus here becomes plus. So it's going to be plus mgx. Alright. And now that we have the Lagrangian, this is where the magic happens. In Lagrangian mechanics, everything is so easy now because everything is practically, you just find the Lagrangian and then the entire problem is solved by just plugging it into this equation, this Euler Lagrange equation you saw in the thumbnail. Q is the generalized coordinate. In our case, we can pick x to be our coordinate. And it's subtracted by this, and it's going to be equal to 0. Okay. So let's take the derivative of each of them. So the partial derivative of the Lagrangian here with respect to x dot is going to be equal to 3/2 m x dot. Everyone still caught up? Perfect. Right? Everyone still caught up, right? mgx here, you take so basically this form will hold good for most classical mechanics problems, including rotational and translational dynamics. That is correct, yes. It does hold up for conservative force, if I'm not mistaken. It holds for conservative force because this form, hold on. This form, right, L equals T minus V, the derivation comes from Newtonian mechanics itself. When you have L equals to T minus V and you plug it into the Euler-Lagrange equation, when you take the derivative of L with respect to Q dot like this, what you're going to get is you're going to get the generalized momentum with respect to that generalized momentum in that Q coordinate. So for example, if this is X, so if Q here is X, there's going to be the generalized momentum in the X axis, so the momentum in the X axis. And then we also have the derivative of L with respect to Q like this. If we take this form, right, if we take this form and take the derivative, what we have is we're going to have derivative of Q t minus v, which is equal to, in this case, t is not directly, the kinetic energy is not going to be directly, it's not going to depend directly on q, the position of the object, or well, the configuration of the object. It only depends on the velocity. So that means this term becomes 0 when you take the derivative. So what you have left is this term. So we're going to have negative partial v by partial q. And if we plug all of this into the Euler-Lagrange equation, we get that d by dt of p is equal to negative v over negative partial v over partial q. In our case, the left-hand side, the rate of change of the momentum is the force. And the right-hand side here is the minus gradient of the potential. And so this, and so the Euler-Lagrange equation, if we use L equals to t minus v here, the Euler-Lagrange equation boils down to just saying that the force acting on something is equal to the minus gradient. That is, yeah. Oh, thanks. There is still quite a delay between chatting and showing up on the screen. Yeah, I've noticed that it's a bit of a problem. Let me see if I can change that. Right now I'm streaming on low latency, but I'm not sure if ultra low is gonna break the stream. The stream not appearing on my front page anymore. Oops. Okay. Let me check ultra low latency. There's a trade-off. Okay. I swear if whoopsies. I may have streamed to the incorrect, I may have accidentally streamed to the incorrect YouTube server. So now it's taking a long ass time for me to send messages between it.